Hi guys, it's your guy Olumide, and today we're gonna be considering another one of the most commonly asked tech interview questions by top tech companies including Google, Amazon, Meta, Netflix, Apple, Microsoft and other top tech companies. Today we'll be considering a highly rated design problem, the L.R.U cache, the least recently used cache. So the problem statement says design and implement a data structure for the least recently used cache that support the following operation. So number one operation that is support is the L.R.U cache class. So this class, we are gonna initialize the class to solve the problem, and the class is gonna be having the capacity, so maximum capacity of the cache, and then it's gonna have a get method. This get method is going to be used to get the value that's associated with a key. It's also going to be having the put method. This put method is going to be used to set key value pair. So it's going to be collecting two arguments, the key, which is an integer, and the value is also an integer. So, and then it's going to set the key value pair within the cache. In the situation whereby the cache has reached or exceeded its maximum capacity, we will need to evict the least recently used element from the cache before adding and inserting the new key value pair that we want. Why? Because the cache is going to be having a fixed capacity, and if adding this new key value pair is gonna exceed that capacity, then we have to remove the least recently used element from the cache. So we're gonna be explaining how to go about this. Let's consider the example. Right here we have an example. So this example is just trying to explain, or just to give an analogy of how the input and output goes. So the input, now let's say we are calling the put method on the on a particular instance of the L.R.U cache class, and this put method we are passing in the key 1 and the value 100. Don't forget the value corresponds to a node, so this 100 is representing the value of the node. So, and then when we put this into the cache, we have one item in our cache. Then we put this also into the cache, which is the key value 250. And after putting this into the cache, then we perform a get to get the value that is associated with the key 2. And after doing that, also we put another key value pair 4 with the node value 300 into the cache. And you see at this point we've added 3 key value pairs into the cache, the key 1, key 2 and key 4. Now we are trying to put in another key value pair, so into the cache here, which is the key 3 and with the associated value 200. But this time is gonna exceed the maximum capacity that is specified in the problem statement over here. So we have to evict the least recently used key value pair from the cache, and the least recently used is this key 1 that's associated with the value 100. Why? Because it's the oldest in the cache, so it's gonna be removed. So when we have our output now, it gives us 250. 250 represents the first get method. Don't forget, put will not return anything. Why? Because we are just performing some insertion, but get is gonna return the value that's associated with a particular key, and if that key is not found, it's gonna return -1. So when we perform the get of 2, it returns 250. Why? Because 250 is the node that's associated, or let me say node value. Node will have the value attribute, so the node value that's associated with the key 2 is 250. And similarly we perform a get of 4 here 2, and then the node value that is associated with key 4 is 300. But right here we perform a get of 1, but because 1 has been evicted. Why? Because at the point here where we input our 4, the capacity have been reached. We inputted 1, 2 and 4, and now in the process of inputting additional 3, we have to evict the least recently used, which is 1. So when we are trying to get 1 now, 1 cannot be found in the cache, the key 1 can't be found, and because of that it returns -1. So that is it. Now this is the example that's given to us along with the problem statement, and now we are going to be explaining how to go about solving this design problem. When presented with a design problem like this, the first step involves understanding the problem and deciding what data structure to use. Let us consider the L.R.U cache below. The L.R.U cache have a capacity of 3, meaning that it can contain 3 nodes or 3 key value pairs, and now we can say that it has reached its full capacity, and we are going to be assuming that the key value pairs are ordered from the least recently used, which is at the far left over here, to the most recently used at the far right, meaning that the one at the far left is the least recently used. It has been the oldest key value pair in the cache, while the one at the far right is the latest key value pair in the cache. So let us try to add a new node or a new key value pair into the cache now. This new pair will effectively be at the most recently used end of the cache, which means that it's gonna be at the far right because it's just coming in and it's the latest. But you see that the cache have gotten to its full capacity containing 3 key value pairs, and because of that we need to evict the least recently used, which is this one right here. We need to evict it so that it can create room for this new pair to enter. And right here, that's it. So we have it evicted and we have this one come inside. So there are 2 operations that we can see that are efficiently used here. The first one is that for the put method, now whenever I want to input a new key value pair into the cache, we first evict the in a situation whereby the cache have reached its maximum capacity, we first evict the least recently used pair from the cache, and then we add the new pair to the cache. So those 2 operations are the basic operations that are involved for the put method, whereby we are trying to put in a new pair into the cache. Now let's walk around the get method that involve retrieving a keys value from the L.R.U cache. So here we realize that whenever we use the get method, we want to retrieve the value that's associated with a key, but then that make it the most recently used key value pair in the cache, because when we retrieve it, you understand, it is now most recently used compared to the others. So we want to move that particular key value pair also to the most recently used end, that is to the further right of the L.R.U cache, and at the same time we want to return the value that's associated with that particular key. So 2 things are involved for the get method as well, is shifting or moving a pair to the most recently used end of the cache, and then returning the value that's associated with that pair. Now we've narrowed the design down into 4 main operations that we discussed just now, and these operations are going to be they are going to lead us to which particular data structure we are going to be using to solve this problem, this L.R.U cache problem. The first 2 operations involved adding and removing a key value pair. So specifically, the first 2 operations involve adding a key value pair to the end of a. Specifically, the first operation involves adding a key value pair to the um, specifically, the first operation involves removing a key value pair from the least recently used end of the L.R.U cache, and the second operation involves adding a key value pair to the most recently used end in a situation whereby the capacity have been exceeded. So we have to remove one in order to insert one. So, and to do this, the best data structure, or let me say one of the best data structure that work for this, is the linked list. Because using linked list, we can add and remove nodes in constant time just by having access to their references. Now the question is, which type of linked list do we use? Is it a singly linked list or a doubly linked list? Adding or removing a node from the head of a linked list, whether singly or doubly linked list, will happen in a constant time because we have immediate access to the head of a linked list, and then we can easily remove the head by referencing the next node, and we can easily add also to the head by referencing the next node. But in a situation whereby we want to add or remove from a tail node, is always gonna take an O(n) time, because even if we have an access to the tail node, to remove the tail node we need an access to the previous node to the tail node, and that will require us traversing the linked list up to the previous node to the tail node. And because of this, we see doubly linked list can do this efficiently. Why? Because it has access to the next node and the previous node. So right from the tail node, we can access the previous node to the tail node and perform any operation without having to traverse the whole linked list. So we will be going with the doubly linked list. An important feature is that we need to be able to access the least recently used node and the most recently used node, because when we are dealing with the first operation whereby we are trying to add a key value pair, a new key value pair, and then the L.R.U cache have been exceeded in capacity, we need to remove one from the least recently used, and we need to add to the most frequently used as well. So in doing that, we don't want to keep traversing the array. So for efficiency, we are going to create a head node and a tail node. So the head node is always going to point at the least frequently used node or end of the L.R.U cache, while the tail node is going to point at the most frequently used end of the cache. So that way, anytime we want to perform a put, we know for sure that put will always be at the most frequently used because it's a new one, it is the latest key value pair, and want to put it there. So we don't have to traverse the whole array to get there. We just have to access the tail node, and we know that tail node will always point at the last node, last frequently used node, and from there we can attach the new pair to the last node. And similarly, if it is overpopulated and we want to remove from the least frequently used, we can access it through the head node, and then we can do the removal instead of having to traverse all about. And this is it. This is what I'm trying to say right here below, where we have the head node pointing at the first the least recently used pair, and the tail node pointing at the most recently. So this way we don't have to traverse. We will bear reference to this tail node and this head node, and from there we can since we are using a doubly linked list, it has a reference to the previous node, so, and as well to the next node. The third operation involves the get method, and it requires us to get a node and to move it to the most frequently used region of the L.R.U cache. And in doing that, it doesn't necessarily indicate that the particular node that we are trying to move is going to be at the head. You understand? When we talk about get, we can get any node. We can decide to get node 2, node 4, node 1. So if it's at the middle now, that means we have to traverse the whole of the linked list until we get to the middle. So is there a way we can do this in a constant time instead? Don't forget, solving DSA problem isn't just about arriving at the answer. It's about explaining your thought process and trying to clarify and show your problem solving skills in front of your interviewer. So they don't really want to see the answer, they want to see the efficiency in how you solve these problems. So now if you look at it and observe well, you will see that each node have a key associated with it. So we can use a hash map to represent this key node pair. We call it key node because they are key connected with nodes. So this node have value, just like here now the node have value 250. So now using a hash map now will enable us to search these things in a constant time. Instead of having to navigate through each of the linked lists, we can just look for the key in the hash map and get its associated value in the hash map. So and the value is gonna be a node. So getting the node, we can easily, we have access to the node already and we can remove it and do anything we want to do with it. So this is what I'm trying to say. We have the hash map, and inside the hash map we have key 1. The key 1 will be, the value will be node 100. So you understand, that node is associated with this particular node in the linked list. And also we have key 2. So and the value of that key 2 will be 250. So whenever we want to try to get the value associated with a particular key, we just have to look into the hash map to get the value associated with it, and from there we can access it inside our linked list. We can access it, delete it, and or probably move it to the most frequently used end of the linked list. So that way it's more efficient. Similarly, using a hash map like that, we can easily get the don't forget that the get method is gonna return the node value. So after by getting, we shift it to the most recently used because we are querying for it. So you have to become the most recently used in the structure, and after that we still have to return the node value because it's a get request. So that way we can easily return the node value that is associated with that key that we are trying to get. Example, now we are trying to get 2. We, after shifting moving the node 2 particularly to the most recently used because a request is done on it, we are also going to return the value of this key, you understand, right inside the hash map, so which is 250. we are going to be returning 250 like that. So that's how we solve the O4 operations. Now we have decided to use the doubly linked list and hash map to evaluate and to represent the L.R.U cache. Now let's see how the put and the get method are going to be evaluated and implemented. This is the flow process for adding a new or an existing key into the linked list. This is the flow process for adding a key value pair into the L.R.U cache. First, we try to check if the key is already in the cache by checking into the hash map. If it is in the hash map, then definitely that node is in the L.R.U cache, that key value pair is there, and because of that we are going to remove this key node from the linked list. So we're going to remove the whole key value pair from the L.R.U cache. Why? Because we in the process of adding, we are adding a new one, so that key must not exist before. We really need to move it to the most frequently used end of the cache. So we are going to remove any existing one from the cache, and then we are going to add the node as the most recently used, and also we are similarly going to add it to the hash map or update it since it already exists in the since the key already exists in the hash map. I'm gonna update it. But in a situation whereby it does not exist in the cache at all, the key does not exist in the cache, we are gonna be adding a new node. We are gonna check if adding a new node will result in overflow. Fine, the key value pair never existed in the cache. Now we are gonna check if the cache is up to its maximum capacity in such a way that adding adding this new pair is gonna result in exceeded capacity. So if it is going to result in exceeded capacity, then we want to remove the least recently used pair from the linked list, and then we want to remove it from the hash map too, because just similarly to how the L.R.U cache must not contain too much capacity than required. The hash map 2 is like a mirror for the L.R.U cache, so it must also have a maximum capacity that the L.R.U cache have. So an institution whereby it has removed the least recently used, it can then now add the node as the most recently used and similarly add it to the hash map too. So but in a situation whereby adding the new pair will not result in overflow, you can just add it immediately and also add it to the hash map. So that's simply how the adding of a pair, how the flow works. So we are gonna see that this logic now, when we start to translate it into code, is gonna be very easy, just like it is now. To further understand how the put method works, that is how the adding of a new pair work. Let's assume we are trying to put in this particular key value pair to the L.R.U cache, and this is the L.R.U cache here. It's already exceeded, the cache is full, so we have to remove the least recently used. So we remove this by calling the remove method. So to remove this, so you see, whenever you want to remove from the head of a node, just because the capacity has been exceeded, so you have to remove before adding, you just need to access head, and that way you can easily remove the least recently used. And that's what we did here. And removing it now, we see that it remains just these two node K2 and K4. So and then we're gonna add what we want to add, which is this new key value pair, and then adding it now, we add it. Adding as well, we only require the tail node. Why? Because it's a doubly linked list, and from the tail node we can access the previous node. So that way we can easily access this previous node and assign its next to this one, so that this will become this new node will become the most recently used node or pair. Similarly, for the get method now, what we do is that in the flow we try to check if the key is in the cache by querying it in the hash map. If it is not in the cache, then we can't get any value associated with that key. We're gonna return -1. But in a situation whereby it is in the hash map, definitely it's gonna be in the L.R.U cache as well. And what we do is that we make the node at this key, you understand, because the hash map will be a key node pair, a key referencing a node. So the node at this key, we are gonna make it the most recently used in the L.R.U cache. And how we are gonna do that is that we are first gonna remove the node. The node existed in the L.R.U cache. We are gonna remove it. We need to place it as the most recently used node. So removing it from anywhere it is before, then placing it in the most recently used node of the linked list. And after doing that, we are gonna return the value associated with this node in the hash map. Don't forget that this particular key references a node. Don't forget, in the hash map is a key node pair. So that node, we are gonna get its value and return it. So let's consider this example for more clarification about the get method. Here we are sending in a key of 2. So and what we do is that we go into our hash map and we try to check if it contains the key 2. If it does not, we return -1, but because it contains it, we are gonna get the node associated with that key in the hash map. So that node, we are going to be able to use that node to reference this particular node in the linked in the L.R.U cache. So it's the same node, you understand? So, and from there we'll be able to remove this particular node, and after removing it, we are gonna add that same node to we are gonna create a new node. We are gonna add that same node because we are performing a get method, so it's not a put actually deal with new node, but get is just about moving the node from anywhere it is in the L.R.U cache to the most recently. So and now we can do that with the linked list, is to delete it here and to add it here at the most recently used end of the L.R.U cache, and from there we now return 250, which is actually the value that's associated with this particular node in the hash map. Don't forget that the hash map contains key node pair, so the value associated is what we are going to return. So now let's move on with the code implementation. We'll be defining a class doubly linked list node. So this is the class that will represent our node, each node in our doubly list link. So, and it's gonna be for the initialization, it's gonna be taking in the value. Don't forget, and the key, don't forget it has a key value pair, so key and the value, so let's call it val. They are both integers, and what we want to do is that we want to set the key attribute and the value attribute. So don't forget the key, just like we have explained so far, and the value also, so value of the node. I also want to set the next attribute and the previous attribute because it's a doubly linked list. I want to set it to none by default, so they are none by default, and very soon we can link them to something in the process of initializing, but by default they are none. So the next thing is, now we have two helper function, the add to tail and the remove node. So the remove node and the add to tail, so there are two helper functions. So let's consider this example to describe and explain how the add to tail helper function works. So let's say we want to add this particular pair to the most recently and most frequently used, which is toward the tail. So it will appear between the previous node. So let's say the node that is previous to the tail is previous node. So the the pair want to add now will appear between the previous node and the tail node. So it's gonna appear after the previous node and before the tail node. Now we are gonna set the left, the previous pointer and the next pointer of the pair we are about to add now. We are gonna set them to their respective previous node and tail nodes to reflect what we just said. So because it will be appearing the new pair, which is 3 pair with the key 3 and then value 200, will appear after this previous node here. So we have this previous node right here, so and it will appear after this previous node, so and before the tail node. So the previous pointer of this new node will be pointing at the previous node, while the next pointer will be pointing at the tail node. Similarly, the next pointer of the previous node will be pointing at the this new node, while the previous pointer of the tail node will be pointing at it. So that way now they have really set up. So to add the tail to the to add the node to the tail or to the end of the linked list, that is the most frequently used end of the linked list, all we have to do is just assign the previous pointer or previous pointer of the new node, set it to reference the previous node, and set the next pointer to reference the tail node, while you set the next pointer of the previous node to reference this new node, and you set the previous pointer of the tail node to reference. So what I'm trying to say in essence is that it's gonna fall between the previous node and the tail node, and while we make those reference relevant and correct. So let's define the helper function add to tail based on the logic that we talked about. So it's gonna be a helper function. Let's create it as a method. So as a method, it's going to take in a node. So it's going to be a doubly linked list node object. So, and then what it's going to do is that that particular node that we want to add, we're going to set, let's first retrieve self.tail. Now let's retrieve the previous node. So that previous node that we talked about, previous node will be self.tail.previous. So here is effectively referring to the previous node to the tail node. So, and don't forget right here, let's quickly add our self.tail. So it's just going to be so now that we have the previous node, we are going to set the previous of this particular node to reference that previous node, just like we explained in the logic. So the new node, we have this previous set to that previous node, and then it will also have its next set to the tail node itself. So self.tail, it will have it set to self.tail itself. So right now, the same thing we apply. The previous node, we have its next node. Previous node, we have its next node set to this particular node based on the logic, and while the tail node itself, we have its previous node set to this. So now they are logged this way. So we see that the previous node is duly set and the next node is duly set. Now we have effectively defined our add to tail method. Now we need to define the remove node method, which is also gonna take in the node that we want to remove, which is also a doubly linked list node. So right now, let's see how to go about this, how to implement this. Now let's consider this example to explain the remove node method. To remove this particular node from this L.R.U cache, now we simply have to, since it is a doubly linked list, we just have to get access to its previous node and then get access to its next node, and then assign both of them their adjacent node to each other, and to come up with this solution. So that way its previous node will link up with its next node, and at the same time the previous node of the next node will link up with the previous node. So meaning that in order to solve this one, we just need to first reference this previous node, after you have a reference to the previous node, so you can then set the next node of the one that you want to remove. You can, after getting reference to the previous node, you can allow that previous node, which is this, so its next attribute won't reference this one you want to remove any longer. It will reference the tail, the next to the next, to this particular one. It will reference it. And similarly, so the previous of the tail now, or let me say the previous of the next of what you want to remove, which is the the previous of the next of this particular node. The next of this particular node is the tail, so its previous will now reference what is here. So in code implementation, what it simply means is that first of all, let's have a reference to the previous node, the node that we want to remove. So a reference to the previous node to this node is given by this. So we can say node dot previous. And now that we have a reference to this previous node, we just take this previous node and then we set its next attribute. Instead of setting it to this node, we set it to node dot next. And similarly, we will take node dot next, which actually reference the tail node. We will now set its previous to instead of setting its previous to node, we will set it to previous node. So that way we have effectively and efficiently removed the node. Now let's create our remove node upper function as well. So this remove node we also have, we take in a node, the node that we want to remove. So, and just like we explained in the logic, what we want to do is that we want to first access the previous node to this node that we want to remove. So this way now we have access to the previous node, and then we will just want the next attribute of this previous node. We don't want it to reference the node itself because we're about to remove it. We want it to reference the next node to it, which in that case is the tail node. And similarly, we want to take the next node to this particular node that we want to remove, which is the tail node. We want to set its previous node away from this node. It was initially the previous node is initially at the node that we want to remove, but now I want to set it to the previous node, and we can simply do that by setting it to previous node here. So this way now we have our two helper function. So now let's move on to create the real class, which is the L.R.U cache class. So don't forget, it's part of the requirement that we have this class L.R.U cache, and it's the whole put method, get method, even all this remove node and add to tail method will be present in the L.R.U cache class as a method to the L.R.U cache class. So we're gonna be collecting the capacity, which is an integer. So don't forget our capacity. So def self.capacity, let's divide into all the capacity, and now we are going to be setting our hash map also. So why we are setting all of this is because this is the initialization stage, and for a single L.R.U cache, for an instance of an L.R.U cache class, that instance can have several multiple put method, several multiple get method, and because of that we need a unique hash map to be storing these puts and gets. So most especially the nodes, the key value pairs. That's why we are having this hash map being defined in the initialization. So also let's have a tail node. Don't forget that we are going to be having a tail node and a head node and the rest of them. So for the tail node now, it will also be a doubly linked list, but this time we can just assign any value to it, because really it's just going to be like a pointer to the most frequently used. So we are not really needing it itself. So similarly to the head now, it will just be a pointer to the most least frequently used this time around. So you can set it to any value, -1. So and what we want to do is that we want to set the head self.head.next equals to self.tail. So this time, we have not made any puts, we have not made any gets, so it just contain a dummy head and a dummy tail that are connected to each other. Similarly, self.tail.next is equals to self.head, but now it will not be next. We want to connect the tail to the it will be a previous. So don't forget, tail represent the last node, so it will only have a previous. Its next will be null. So similarly, head have only next, it doesn't have a previous. So this is all that we will be having in our initialization, at least for now. So now let's go on to create the get method. Now the get method, we take in a key, so to signify that I want to get the value associated with that key. So and what we want to do is that we want to first of all check if key is present in the hash map. So if the key itself is present in the hash map, so well, fine, let's just use this condition that if not key in the hash map. So in situations whereby key is not in the hash map, we want to return -1. So if it's not in the hash map, so but if it is, we can now continue in a situation whereby it is, and if it is, definitely there exists the corresponding node, or let me say the node value of that key exists in the L.R.U cache. So we want to remove, just like we explained, want to remove node of hash map of that key. Don't forget, hash map of key is gonna reference self.hash map of key is gonna reference the particular node that we are trying to get. So why we are removing it is because it is now going to be at the most frequently used. So we are removing from wherever it is in the linked list, and now we'll be adding it to the add to tail. We'll be adding it to the most to the tail, which is the most frequently used now. So, and that's what we are doing. And in a situation like that, after that, we are gonna return hash map of key, so dot value. So why hash map of key reference the node, and we need the node value, so that's why I did that. So you will see that we are using this two helper function, the remove node and the add to tail. So we are gonna be, let's quickly move the whole stuff. Let's move the whole stuff from here. This is where it is needed the most. So this is where it is needed the most. So we are putting it here, so we can easily access it as a method. So easily access it as a method. So I hope you understand what we did right here. So it's a method to the L.R.U cache class. So now let's define our put also. The put is gonna take in the key. Don't forget, this self that we are putting there is referring to the instance that is calling the method. So that's how it's meant to be. So we have our key integer, and we have our value. We are passing our value as an integer, and what we're doing now is that we are gonna be checking if if this particular key exists in the hash map. So if it exists, fine, we want to remove it because we don't want to have more duplicate keys. Self.remove, so we don't want to have conflict. So we are removing the hash, the particular node that is associated with this key. We are gonna be removing it. So, and after that, we are now going to, let's try and create now this node. Now that we are sure that it has been removed and never existed in the L.R.U cache, we are going to be creating a new node. So using this key and this value, so that will create a new node for us, and now we can now add it to our hash map. So hash map of key is equals to this node. So is a key node pair, and after adding it, now let's try and check if the length of our hash map, if the length is less than self dot. So okay, let's look at a real condition. So a situation whereby it is greater than it, so we can place a condition under a statement under it. So self.capacity. So this is a situation whereby the length of the hash map is now greater, meaning that it now contains more key value pair than the capacity that the L.R.U cache is supposed to contain. And in a situation like that, what we want to do is to remove the key, the key value pair at the least recently used end. So that's what we want to do, and we are gonna call the function in situation whereby it is greater than it, we're gonna call self.remove node of so here I'm gonna be passing self.add dot next. So why we are doing this is that we really, self.add is derived from time, so and is meant to point at the next, which is going to be the least recently used cache. So, and that is why we now remove the least recently, and this is the way to remove the least recently, the one that is immediately next to the add node. So, and also want to delete it from the hash map, so that way hash map is gonna be less than the capacity to, or at least equals to the capacity. And by then we can, in a situation whereby it is less than or equal to it, we can easily add to it, you understand. So knowing that in the process of adding, it won't be greater than the capacity that is meant to carry. So we're gonna be deleting self.hashmap of, so what we need a key now, and the key must correspond to the head that we are trying to the least recently used stuff that we are trying to get. So but one thing you will notice right here is that by the time I call self.remove node, it's gonna remove the node that is next to the head node, which is the least recently used, and definitely the head node is gonna be pointing to a new node. You understand? Don't forget the remove node is gonna remove it and make sure that it points to the next one. So and because of that, by the time I'm trying to access the head.next, it's gonna be accessing a new one. So because of that, we really need to call this delete function first before we call the remove node, so that it can reference that particular node, that particular least frequently used node that we want it to reference. You understand? Because in the process of removing node, calling this function below is gonna remove the node permanently from the list link, and if it removes the node and we now later go and call the delete hash map, is going to be deleting another node. So we really need to delete from the hash map so that it could reference the correct node, and after we have referenced and used it, we can now delete it itself. So you see how you place code really matters, and logic actually simplify things for you. So it really tell you what you have to do, what you are meant to do. So okay, and after you have done all of that, we can now add to the tail. And what are we adding? A particular node that we created. So don't forget that we created the node, we had the node to the key value pair to the hash map, then we try to check if upon adding it is not greater than the capacity. So at least it should be equal to it or less than it, so that it can accommodate this one, so that at least we will know that the node the L.R.U cache 2 is not greater, it is either less than or equal to it. So and by then we did this. So this is all we need to solve this problem now. So right here is the solution. So let us create an instance. So cache 1 is equals to L.R.U cache. So let's pass in a capacity of 3 to it, and after doing that we want to input some things into our cache by calling the put method, and we are going to be passing a key of 1,100. So similarly, let's pass in a key of 2,250, a key of 4,300, so a key of 3,200, and let's perform a get. Cache 1 dot get 1. Let's get the key of the value 1. So we are gonna be printing it, so you can see the answer. Alright guys, when I run the code, I encounter some little error that is attributed to me writing hash map alone. So hash map is not supposed to be written alone, so anywhere that you see that hash map is written, convert it to self.hashmap, because hash map is an attribute in the class, in the L.R.U cache class. So I made the mistake of writing hash map. So anywhere you see hash map, convert it to self.hashmap, so it's an attribute. So and after doing that, converting every occurrence of hash map to self.hashmap, if you run the code, you will get -1, and that is very correct, because -1 has been replaced. It is the least recently used in this instance. Why? Because first of all, the pair 1 is added, then pair 2, then pair 4, then pair 3. So that is more than the capacity that we have, which is 3. So because of that, 1 has been removed, and by the time it's removed, it returns -1, because that's what we had to do. But if you put in 2, you're gonna be getting 250. Like here, this is it, 250. So that's it. Make sure you convert every hash map that was there before to self.hashmap. So, and that's it, the L.R.U cache. So it's a design problem, and that's why it takes so long to solve, but I make it more clarified and more interesting. So thank you, and enjoy your day.